Welcome to this coding walkthrough. Today, we'll be tackling LeetCode problem number 621, titled Task Scheduler. This problem focuses on efficiently scheduling tasks while adhering to a cooldown period. It's a great exercise to strengthen your understanding of greedy algorithms and hash maps. Let's dive in. In this problem, you are tasked with scheduling the execution of various tasks represented by characters. Each task takes exactly 1 unit of time to complete. However, if the same task is repeated, it might require a cooldown period between consecutive executions. The cooldown period is represented by an integer n, which specifies the minimum number of idle units the CPU must wait before the same task can be executed again. The challenge here is to calculate the minimum total time required to complete all the tasks, including any idle periods. For input, you are given a list of tasks as characters, where the length can range from 1 to 10,000, and the cooldown integer n, which falls between 0 and 100. The output should be a single integer representing the total time required. To illustrate how the scheduling works, let's consider the first example. Here, the input tasks are B, and the cooldown period n is 2. This means that after executing a task, at least 2 units of time must pass before the same task can be repeated. One valid execution order is A, B, idle, A, B, idle, A, B. In this sequence, the CPU waits for idle periods to respect the cooldown constraint. The total time taken in this case is 8 units. Now, if we change the cooldown period to 0, as shown in the second example, tasks can be executed consecutively without any idle periods. The order becomes A, B, and the total time is reduced to 6 units since there's no need to wait. Let's look at another example where the input tasks are B, C, and the cooldown n is 2. In this case, a valid execution order is A, B, C, A. Notice that we alternate between different tasks to minimize idle time while still respecting the cooldown period. The total time required here is 8 units. This demonstrates how the task scheduler can optimize the order of execution to achieve the minimum possible time while adhering to the cooldown constraints. Finally, let's summarize the constraints and edge cases you need to consider while solving this problem. The input list of tasks has a length that ranges between 1 and 10,000, and the cooldown period n is a non-negative integer between 0 and 100. Each task is represented by an uppercase English letter from A to Z. A few edge cases to note include scenarios where n is 0, meaning there's no cooldown and tasks can be executed consecutively. On the other hand, if all tasks are the same and n is greater than 0, the CPU will be forced to remain idle between executions. Lastly, if there are many distinct tasks, the CPU might never need to be idle since it can always execute a different task while waiting for the cooldown of others. These considerations will help you design an efficient solution. To solve the task scheduler problem, the goal is to determine the minimum time required to execute all tasks while adhering to the cooldown constraint n. One approach we can consider is the brute force method, which involves simulating the scheduling process step by step. The intuition here is straightforward. We process tasks in the order they appear, ensuring that each task respects the cooldown period before being executed again. This can be implemented using a queue or array to track when each task becomes available. At every time unit, we check which tasks are eligible to run, prioritize them, and then either execute one or remain idle if no tasks are ready. However, this approach has significant drawbacks. Its time complexity is O(T*n), where T represents the total number of tasks, and n is the cooldown period. This inefficiency arises because we repeatedly check task availability at every step. Additionally, the space complexity is O(n), due to the need to track cooldown states. While this method is conceptually simple, it becomes highly inefficient as the input size grows, especially when there are many idle states to be simulated. Now, let's consider a more optimized approach based on a greedy strategy combined with frequency counts. The intuition here is that tasks with higher frequencies act as bottlenecks in the schedule, as they must be spaced out to satisfy the cooldown constraint. By prioritizing these high-frequency tasks, we can minimize idle slots and distribute the workload more effectively. The implementation involves several key steps. First, we count the frequency of each task using an array or hash map. Next, we identify the task with the maximum frequency, denoted as f_max. This task determines the minimum schedule length because it requires spacing out its occurrences with n idle slots between them. We then arrange these f_max tasks with the necessary spacing and fill the idle slots with other tasks wherever possible. If additional tasks remain after filling all idle slots, we append them to the schedule. The time complexity of this approach is O, t plus k log k, where t is the total number of tasks, and k is the number of unique tasks, with the sorting step contributing to the logarithmic factor. Space complexity remains O, k, due to the storage of frequency counts. A key observation here is that if the total number of tasks exceeds the idle slots dictated by f_max, the task list itself imposes the primary limitation. This makes the greedy approach both efficient and practical. An even more efficient strategy involves mathematical optimization, allowing us to compute the minimum required schedule length directly. This avoids simulating the scheduling process entirely. The key formula is as follows: the minimum schedule length equals the maximum of two values. The first value is f_max 1 n plus 1 plus tasks with f_max, where f_max is the frequency of the most common task, n is the cooldown period, and tasks with f_max represents the number of tasks sharing that maximum frequency. The second value is simply the total number of tasks. This formula accounts for both the spacing required by the most frequent tasks and the possibility of additional tasks filling idle slots. While this approach is highly efficient in terms of time complexity, it comes with trade-offs. Specifically, the reliance on a formula can make the solution less flexible and harder to generalize or debug compared to other methods. For this problem, we ultimately select the greedy approach with frequency counts as our chosen strategy. This method strikes a balance between clarity, efficiency, and flexibility. It avoids the inefficiencies of brute force simulation while remaining intuitive and easy to implement. By focusing on prioritizing bottlenecks, this approach effectively addresses the problem's constraints without overcomplicating the logic. The solution hinges on a few key insights. First, the minimum schedule length is determined by the task with the highest frequency. Tasks with lower frequencies or idle slots can be dynamically filled in around this bottleneck. Sorting tasks by frequency not only simplifies this process but is also computationally inexpensive, making it well suited for this problem's requirements. Compared to the brute force simulation, this approach is significantly faster and more scalable for larger inputs. While mathematical optimization is marginally faster, it sacrifices transparency and can be harder to adapt for variations of the problem. The greedy strategy with frequency counts offers a strong middle ground. Its time complexity of O, t plus k log k, ensures efficiency, where t is the total task count and k is the number of unique tasks, while its space complexity of O, k, keeps resource usage manageable. This method delivers a robust and systematic solution, providing clarity in implementation without compromising on performance. The task scheduler problem revolves around scheduling tasks such that the total time required is minimized, while respecting a cooldown period between tasks of the same type. For example, if we have tasks A, B, and C, and a cooldown period of 2, we need to determine the optimal order to execute them while adhering to this constraint. The first step in solving this involves counting the frequency of each task using a hash map. By knowing how many times each task appears, we can understand which tasks will have the greatest impact on the scheduling. For instance, in our example, the frequency map would be A3, B2, C1. Next, we sort these frequencies in descending order, which gives us an array like 3, 2, 1. This helps us identify the most frequent task, which will play a key role in structuring the schedule. Finally, we calculate the ideal time slots required for the most frequent task. If the task with the highest frequency appears 3 times, and the cooldown period is 2, we can calculate the gaps it creates between occurrences, which will guide the rest of the scheduling process. To determine the number of idle blocks required, we use the formula idle_blocks equals max_frequency 1 n. This accounts for the gaps between occurrences of the most frequent task, as the last occurrence doesn't need a trailing cooldown. For example, if the most frequent task appears 3 times and the cooldown period is 2, the idle blocks would be 3 to 1 *2 equals 4. Once we have these idle blocks, we try to fill them with other tasks. For each remaining task frequency, we reduce the idle blocks using the formula idle_blocks equals min, max_frequency 1, frequency. This means that tasks with lower frequencies can fit into the gaps created by the most frequent task. If the idle blocks become negative, it indicates that there are more than enough tasks to fill the gaps, so we set idle blocks to 0. Finally, the total time required is calculated as the sum of the number of tasks and any remaining idle blocks, using the formula total_time equals len, tasks, plus idle_blocks. This gives us the minimum time needed to schedule the tasks while respecting the cooldown constraints. The total time formula ensures that we account for both the tasks themselves and any idle periods that remain unfilled. A key insight here is that the task with the highest frequency largely determines the structure of the schedule, as it creates the gaps that need to be filled. The number of idle slots depends on the cooldown period and how well the other tasks can fill these slots. If all gaps are filled, meaning idle blocks become 0 or negative, the total time simplifies to just the number of tasks. To implement this approach, we use a hash map to store task frequencies and a heap or sorted list to prioritize tasks by their frequencies. It's also crucial to handle edge cases. For instance, when all tasks are unique, such as tasks equals a, b, c, with n equals 2, there are no idle periods, so the total time equals the number of tasks. On the other hand, if there's a high cooldown period and repeated tasks, like tasks equals with n equals 3, we may need large gaps to meet the cooldown requirement. In scenarios where other tasks can fill all the idle slots, the scheduling becomes more efficient. For example, with tasks equals a, b, c, and n equals 1, the idle slots created by the most frequent task are completely filled by the other tasks, minimizing the total time. The complexity of this algorithm is important to understand. Counting the frequencies of tasks takes n, where n is the total number of tasks. Sorting the frequencies requires m log m, where m is the number of unique tasks. Filling the idle blocks is an m operation. Therefore, the overall time complexity is n plus m log m. Space complexity is m, as we store the task frequencies in a hash map. These analyses ensure that the solution is efficient even for large inputs. Let's now look at a specific example to see how this works in practice. Consider the input tasks equals b, c, with n equals 2. First, we calculate the task frequencies, which are 3, b, 2, c, 1. Sorting these frequencies gives 3, 2, 1. The task with the highest frequency is which appears 3 times. Using the formula for idle blocks, max_frequency 1 n equals 3 to 1 2 equals 4, we calculate that 4 idle slots are needed. We then fill these slots with other tasks. Subtracting the frequency of b, we reduce the idle blocks by 2, leaving 2 idle slots. Subtracting the frequency of c, we reduce the idle blocks by 1, leaving 1 idle slot. Finally, the total time required is len, tasks, plus idle_blocks equals 6 plus 1 equals 7. This means the minimum time to execute all tasks is 7. The output is therefore 7. Here, we start by importing the necessary modules, counter from the collections library to count the frequency of each task, and heap for managing a max heap. First, we define the least interval method, which accepts the list of tasks and the cooling interval n. Our goal is to determine the least amount of time required to complete all the tasks while respecting the cooling interval. To do this, we use the counter class to count how many times each task appears. Then, to easily access the tasks with the highest frequencies, we create a max heap. Since Python's heap module only supports min heaps, we store the negative values of the frequencies to simulate a max heap. After initializing the heap with these negative frequencies, we call heap.heapify to organize the heap structure. We also initialize a variable time to 0, which will keep track of the total time taken. Now, as long as there are tasks left in the heap, we process them in cycles. Each cycle can handle up to n plus 1 tasks, representing the cooling interval plus 1 task slot. For each cycle, we use a temporary list temp to store the tasks we process. If the heap is not empty, we pop the most frequent task from the heap and add it to temp. This ensures we prioritize tasks with the highest remaining frequency. Next, we adjust the frequencies of the tasks processed during the cycle. For each task in the temp list, we check if the remaining count of the task is greater than 0. If it is, we push the updated frequency back into the heap, again as a negative value. This ensures the task will be reconsidered in future cycles if it still has remaining instances. Once all tasks in this cycle are handled, we increment the time variable. If the heap is not empty, meaning there are still tasks left to process, we add the full cycle duration of n+1 to the time. If the heap is empty, we simply add the number of tasks processed in this cycle, since we don't need to wait for the cooling interval. Finally, after exiting the loop, we return the total time. This gives us the minimum time required to complete all tasks while respecting the cooling interval, ensuring that the most efficient scheduling is achieved. Here, we begin by importing the necessary Java utilities and defining our solution class with the least interval method. The first step in the method is to count the frequency of each task. To do this, we use a hash map where the keys are the task characters and the values represent their respective counts. As we iterate over the input tasks array, we populate this map using the getOrDefault method to handle the case where a task is not yet in the map. Next, we use a max heap, implemented with a priority queue, to efficiently process tasks with the highest remaining frequencies. The max heap is initialized with a reverse order comparator to ensure that the highest frequencies are at the top. We then add all the task frequencies from the map into the heap. The variable time is initialized to track the total time taken to complete all tasks. Now, we enter a while loop that continues until the heap is empty. Inside the loop, we use a temporary list to store the frequencies of tasks being processed in the current cycle. For each cycle, we attempt to process up to n+1 tasks, either by pulling tasks from the heap or moving forward if the heap is empty, as shown in the for loop. After processing tasks in the current cycle, we iterate through the temporary list to decrease the frequency of each task by 1. If a task still has a remaining frequency greater than 0, we add it back into the max heap. This ensures that tasks with remaining counts are reconsidered in future cycles. Finally, we update the time variable to reflect the duration of the current cycle. If the heap is empty, the cycle duration is simply the number of tasks processed, stored in temp.size. Otherwise, we add a full cycle duration of n+1. This accounts for any idle time needed to respect the cooling interval. Once the heap is empty, meaning all tasks are completed, we exit the loop and return the accumulated time. This ensures the minimum time required to execute all tasks while adhering to the cooling interval constraint. Here, we are given the tasks B, with a cooldown period of n=2. The goal is to determine the minimum time required to complete all tasks while ensuring no task is executed more than once within its cooldown period. To begin, we count the frequency of each task using the counter class, resulting in 3b3. Next, we build a max heap from these frequencies to efficiently access the most frequent tasks. Since Python's heap library only supports min heaps, we store the negative of frequencies, giving us max_heap equals -3 - 3. This setup allows us to systematically process the tasks while adhering to the cooldown constraint. Now, we proceed with the task execution in cycles. In cycle 1, with time starting at 0, we process up to n+1 or 3 tasks. We first pop -3 for task A, decrementing it to -2, then pop -3 for task B, also decrementing it to -2. Since both tasks still have remaining counts, we push -2 back into the heap for each. The max_heap at this point becomes -2 - 2. This cycle takes n+1 equals 3 units of time. In cycle 2, at time equals 3, we again process up to 3 tasks. We pop -2 for task A, decrementing it to -1, then pop -2 for task B, decrementing it to -1. Both are pushed back into the heap as -1 each, resulting in max_heap equals -1 - 1. This cycle also takes another 3 units of time. In cycle 3, starting at time equals 6, we process up to 3 tasks one final time. We pop -1 for task A and decrement it to 0, then pop -1 for task B and decrement it to 0. With both tasks now completed, there are no remaining counts to push back into the heap, leaving max_heap empty. This cycle adds 2 units of time, as only 2 tasks were processed. Summing up all the time spent across the 3 cycles, the total time required to complete all tasks is 8. In this example, we have tasks A, B, C, D, with n equals 2. The task frequencies are 3, B, 1, C, 1, D, 1. To begin, we build a max heap from these frequencies, resulting in max_heap equals -3, -1, -1, -1. Starting with cycle 1 at time equals 0, we process up to 3 tasks. We pop -3 for task A, decrementing it to -2, then pop -1 for task B, decrementing it to 0, and pop -1 for task C, also decrementing it to 0. Since task A still has a remaining count, we push -2 back into the heap. The updated max_heap is -2, -1. This cycle takes 3 units of time. In cycle 2, starting at time equals 3, we continue processing the remaining tasks. We pop -2 for task A, decrementing it to -1, then pop -1 for task B, decrementing it to 0. Task A still has a remaining count, so we push -1 back into the heap, leaving max_heap equals -1. This cycle adds another 3 units of time. Finally, in cycle 3 at time equals 6, we process the last remaining task. We pop -1 for task A, decrementing it to 0. With no more tasks left to process, the max_heap becomes empty. This cycle adds 1 unit of time. The total time required to complete all tasks is therefore 7. In this example, we have tasks of B, C, D, with n equals 2. The task frequencies are 1, B, 1, C, 1, D, 1. Building the max heap from these frequencies gives us max_heap equals -1, -1, -1, -1. With time starting at 0, we execute all 4 tasks in a single cycle. We pop -1 for each task A, B, C, and D, decrementing their counts to 0. Since all tasks are completed in this cycle, the max_heap becomes empty. The total time taken for this example is simply the number of tasks, which is 4. These examples illustrate how the algorithm effectively handles different distributions of tasks while always respecting the cooldown constraint. By prioritizing the most frequent tasks with the max heap and efficiently managing cycles, the solution ensures minimal total time is spent to execute all tasks. To analyze the time complexity of this solution, let's break it down into key steps. First, we count the frequencies of tasks using the counter class. This operation iterates through the list of tasks once, making it O, M, where M is the total number of tasks. Next, we construct the max heap using heap.heapify. The heap contains one entry for each unique task, so this step has a time complexity of O, K, where K is the number of unique tasks. The most complex part of the algorithm occurs in the while loop, where we process the heap. In each cycle, we process up to n+1 tasks. Since popping and pushing to the heap each take O log K, the total cost per cycle becomes O, n+1, * log K. Over the course of scheduling all M tasks, the number of cycles is proportional to M, leading to an overall cost of O, m * log K, for heap processing. Combining these steps, the total time complexity is O, M, plus O, K, plus O, m * log K. Since M usually dominates K, the final time complexity simplifies to O, m * log K. The space complexity of the solution is determined by several components. First, the counter object stores the frequency of each unique task, requiring O, K, space, where K is the number of unique tasks. Then, the max heap, which stores up to K elements, also contributes O, K, space. Additionally, during each cycle of task execution, we use a temporary list called temp to hold up to n+1 tasks. In the worst case, this list requires O, n, space. When we combine these components, the total space complexity becomes O, K plus n. However, since K, the number of unique tasks, is typically much larger than n, the space complexity simplifies to O, K. When comparing this optimized heap-based approach to a brute force method, the differences in efficiency become clear. A naive approach would involve simulating each time unit and checking which tasks can be executed. This requires iterating through all tasks repeatedly, leading to a time complexity of O, m squared, which becomes prohibitively slow for large inputs. In contrast, the optimized approach leverages the max heap to prioritize task execution, reducing the complexity to O, m asterisk log k. This improvement is especially significant when the total number of tasks, m, is large, but the number of unique tasks, k, is relatively small. By focusing on k instead of m in certain operations, the optimized solution achieves far greater efficiency. To further understand the behavior of this solution, let's analyze the best, average, and worst cases. In the best case, where n equals 0, there is no cooldown period, and tasks can be executed sequentially. Here, the time complexity simplifies to O, m plus k, since we only need to count frequencies and build the heap once. For the average and worst cases, when n is greater than 0, the heap is actively used to manage task execution. The dominant operations involve pushing and popping tasks from the heap, each taking O, log k. Since every task is processed this way, the overall time complexity becomes O, m asterisk log k. Mathematically, the heap operations dominate the other steps, as each task is pushed and popped from the heap at most once. Adding the costs of frequency counting and heap construction, the final complexity remains O, m asterisk log k, confirming the efficiency of this approach even under the most demanding scenarios. In this section, let's look at some common mistakes people make when solving the task scheduler problem and how to avoid them. First, there's often confusion around the cooldown period. Remember, tasks only need to wait in units of time if they are being executed again within the cooldown window. This misunderstanding can lead to overestimating the total time required. The solution is to carefully track when tasks are executed, which can be done efficiently using a priority queue or a cooldown map. Next, idle time is another area where many solutions go wrong. Either they underestimate how much idle time is needed, or they overcompensate. To handle this properly, focus on the frequency of the most common tasks and calculate the required idle slots to ensure the cooldown is satisfied. Another mistake is sorting tasks by frequency directly, which can unnecessarily complicate the implementation. Instead, use a max heap or a frequency map to manage task scheduling efficiently. Finally, beginners sometimes overcomplicate edge cases, like when the cooldown is 0 or when all tasks are unique. For instance, if n equals 0, there's no cooldown, so tasks can execute consecutively. And if all tasks are unique, the total time is simply the number of tasks. By simplifying these scenarios, you can avoid introducing unnecessary complexity into your solution. Now, another common pitfall is ignoring optimal patterns. Some solutions attempt to brute force all possible task orders, which is highly inefficient. The key is recognizing that the optimal strategy always involves minimizing idle time by prioritizing tasks with the highest frequencies. This brings us to some insights that are especially helpful in an interview setting. The core of the problem lies in task frequencies and minimizing idle slots. By focusing on the task with the maximum frequency, you can structure the solution around it. A good way to think about this is as a bottleneck problem. Identify the most frequent task, then calculate how to arrange the other tasks around it to minimize idle time. It's also important to be prepared for edge cases during interviews. For example, scenarios like n being 0, having tasks with equal frequencies, or dealing with very large cooldown values are commonly tested. Finally, be ready to explain the trade-offs in your approach. For instance, why using a max heap or a frequency map is more efficient in terms of time complexity compared to a brute force solution. Being able to articulate these trade-offs demonstrates a strong understanding of the problem. Let's now connect the task scheduler problem to some related problems you might encounter. These include LeetCode problem 767, reorganize string, which involves rearranging characters in a string so that no two adjacent characters are the same. The constraints here are similar to those in task scheduling. Another related problem is 358, rearrange string k distance apart. This requires rearranging a string such that the same characters are at least k distance apart, again echoing the idea of maintaining a cooldown period. Lastly, problem 1057, campus bikes, is a greedy pairing problem that shares similarities in terms of prioritization strategies. Moving on to alternative approaches for solving the task scheduler problem, the first is a greedy method that uses a frequency map. Here, you count the frequency of each task, prioritize based on frequency, and calculate idle slots directly. This method is both simple and efficient, running in O, n, time, but it requires careful attention to idle slot calculation. On the other hand, the max heap approach uses a priority queue to repeatedly schedule the most frequent task while respecting the cooldown constraints. While this method is slightly slower, with a time complexity of O(n) log n, it's often easier for many to implement. Both approaches have their trade-offs, so it's important to choose the one that aligns best with your strengths and the problem requirements. Finally, we have the simulation approach. This method involves simulating each unit of time and executing tasks as they become available. While it's an intuitive way to solve the problem because it directly mirrors the scheduling process, it can be highly inefficient. In the worst case, it has a time complexity of O(n squared, so it's generally not recommended for large inputs. However, understanding this approach can still be valuable, as it helps solidify your grasp of the problem's mechanics and constraints. The key takeaway here is to focus on approaches that balance efficiency with clarity, and to always be mindful of the trade-offs involved in your chosen method. Great job! We've successfully tackled the task scheduler problem, exploring efficient scheduling strategies with heaps and queues. I hope you found this walkthrough valuable. Remember to keep practicing and applying these concepts to similar problems. Thanks for watching, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!